Hello. So today I'm going to make a very brief video on the synthesis of Pentaborane 9 or 11 from diborane. Now, diborane is an industrially available gas, meaning that you can buy it on Alibaba, or it's produced in reasonably small quantities, but it's commercially available, whereas Pentaborane, not so much. It's very little use for it. So, again, in our previous video, we went over why Pentaborane is a great fuel for afterburners, ramjets, and/or rocket engines. So here's some important highlights from a paper on Pentaborane pyrolysis from diborane. So the way you produce Pentaborane is by taking diborane with a 1:5 ratio of diborane hydrogen and flowing that through a reactor at about 240 degrees. Now, I highlighted something very interesting here, which is that modifications to the present system, such as progressively increasing the reactor volumes, variation in the flow rate and temperature, and variation in reactor volume with increasing temperature, no advantageous effects in increasing the percentage of diborane to pentaborane. What appears to be the case is that higher pass rates through the reactor are the primary determinant of the conversion rate. So going from 30% for 9-4 passes to 83% for 168 passes. In the paper, they found that there was really no catalyst that could accelerate. The use of a catalyst to accelerate certain desirable reactions in the synthesis of pentaborane and decaborane had been examined by Whitney. Small catalytic effects were observed with alumina, but these were not directional towards the desirable product. This is not surprising, since a desirable catalyst would have to be extremely complex in order to cleave the molecule directionally, dehydrogenate it, and then rearrange the radicals to their required higher hydrate. So it's not a catalytic process. It appears that it's a very simple process whereby you're increasing the chain length of the borane molecule. And all that is required is passing that. It's basically like ammonia synthesis. Now, is it endothermic? Apparently not. Exo. We don't see any data on exothermicity or endothermicity. But considering that it needs to be kept at 240 degrees Celsius, we would assume that it is endothermic, meaning that heat must be applied. And so, for those interested in borane synthesis or pentaborane synthesis, now one thing to finish that off, definitely check this paper out. The last thing is that when you synthesize it, you're not going to get pure pentaborane, as we find here. So it's cooled in solid carbon dioxide, 2 atmospheres. Then from another patent, what I found was that you're going to get a byproduct that will have to be separated out or condensed out through distillation. After distillation of the volatile fractions, the solid hydrides were removed from the reactor and traps and analyzed. Decaborane was removed by washing out the apparatus with benzene and estimated by the quinoline color reaction. So here is the apparatus for pyrolysis of diborane. So again, you're just basically going through multiple passes under high temperature at a 1:5 ratio of diborane hydrogen at about 250 degrees Celsius. And that's about it. It's a very simple process. You may ask why you haven't heard of this fuel, or you have not. Yeah, I mean, it's a good question considering that it has 1.7 times. Let me do the math right now. So 68 divided by 42.8, 1.6 times. Yeah. I think it's 69. We can double check that in the Energy Density Bible by Friedis. So let's go up here. Try to find. I can't find it. Okay, sorry about that. We will open up Friedis. No, I guess that's okay. We will open this guy up. Actually, we'll open it up in Chrome, since we prefer Chrome. Pentaborane. Okay. 67.67, so 68. Diborane, 73.6. So, that is roughly 1.58 times. Now, the only issue is when, alright, let's go to zip fuel. Alright. Okay, fuel burns to create solids that are both sticky and corrosive, while boron carbide solids are abrasive. This causes serious problems for turbine blades and jet engines. So that's one disadvantage. Particulates allowing the aircraft to be spotted visually at long range. But again, this is not what this fuel is going to be. This fuel is going to be for hypersonic ramjets. Right? What you're doing here is, well, we know how a ramjet works. If your fuel has 70% more or 60% more energy density, that makes a big difference. Well, you can fly it about 60% longer. Because in this case, volume is almost more important than mass in this case, because you're dealing with very high wave drag. Right? So wave drag is the main determining factor at sonic speeds. And so if we go to so this is actually going to start a business making Pentaborane fuel. You can see here that so they talk about here elemental boron is a highly attractive fuel for propellants and explosives. Now these values are over 3 times higher per unit of volume and 1.4 times higher per unit of mass than those of hydrocarbon fuel. Now they're referring here to pentaboranes, so it's got much higher volumetric energy density, which is very important at those supersonic speeds where wave drag is the main determining factor. So for rocket fuels, where you're using an oxidizer, in a rocket fuel, a rocket engine, you have this big chamber, you have your turbo pumps, right? Pentaborane oxygen difluoride has a specific impulse of 466 seconds. Now, nitrogen tetroxide hydrazine blend, 350. Right, so that's going to be all your ICBMs, right? Russian, Chinese, intercontinental ballistic missiles are all using, right? N2O4 UDMH. And typically it's a mix of anhydrous hydrazine and unsymmetrical dimethyl hydrazine. Okay, so higher specific impulse. I mean, you're basically, my recording stopped because I am too cheap. Actually, I don't have the money to upgrade my Bandicam. Now, you were getting the specific impulse of liquid hydrogen without their cryogenic disadvantage and the bulkiness. The fact that hydrogen takes up so much room, that means there's more tank weight. The whole fuel system is more elaborate. You're going to lose a lot of the fuel and boil off, which is not a big deal because it's cheap. But it can't be used for essentially on demand, where you have a missile and you have to launch it any second. You can't exactly fill it up with liquid oxygen, liquid hydrogen, and then leave it to boil off when you need to launch that missile. That's not going to work. So I am of the belief that this borane fuel will be resurrected from the 1960s and used in specific defense aerospace applications. That's going to be pulse jets, or I should say ramjets, ICBM fuels, and potentially even using it in an afterburner on a jet aircraft. Because again, if it's got higher energy density, you're going to burn a lot of that fuel in your afterburner when you're taking off from your aircraft carrier. If that fuel's lighter, that's just better for everything. And so it's worth the cost. I mean, aircraft designers will spend a huge amount of effort to reduce the weight of a bracket. For example, an engine mounting bracket. I don't know if anybody happened to follow that GE engine bracket competition. So if you have a fuel that's 60% more energy dense, that's sort of groundbreaking, right? I mean, that's a major improvement. So anything that can get away with essentially bypassing that limitation of the solid particles produced, that would obviously destroy turbine blades or render it impractical for use in a internal combustion engine, for example. It can be burned, right, in a rocket engine or a ramjet. Or even something like that British aircraft that I keep forgetting the name of. It's this liquid hydrogen-powered supersonic air vehicle that uses a pre-cooler, uses the liquid hydrogen on board to pre-cool the air coming in. I think it's compressorless. I think it might have a compressor. I don't know. Correct me if I'm wrong. But these kinds of futuristic air vehicles, I think, would really, really benefit from using pentaborane fuels. But granted, it's toxic. But look, hydrazine is the best rocket fuel. It depends. I mean, some people disagree, but it's really the best you can get, because you don't want a cryogenic oxidizer or cryogenic fuel. It's just too much hassle. So I think I'm really bullish on this fuel being used in niche applications. It's something that really sort of working hard to understand the synthesis process and understand all of the necessary details to really and manufacture small pyrolysis machines as well. I hope to be the first one to make a small pyrolysis machine to produce it. So yeah, that's about all I have to say for today.